morning. My name is James Dow, and my presentation today is cobalt chromium alloys, and specifically cobalt chromium alloys used in electron beam manufacturing. And on the left side of the slide here, there's a picture of a knee implant, which is what they use or what they can manufacture mostly through electron beam manufacturing, either hip and knee implants or aluminum die casting tooling. So the research paper was titled Phase and Grain Size Inhomogeneity and Their Influences on Creep Behavior of Cobalt, Chromium, Molybdenum Alloy Additive Manufactured by Electron Beam Melting. The research is fairly new. It was done in 2015, and the scope of the experiment was to investigate the microstructure in homogeneity and its effect on creep behavior along the EBM build direction. So electron beam melting is similar to SLS process, but it uses electrons rather than laser and light. So it builds parts in the vertical direction, and they wanted to look at how the grain microstructure varies in this direction and how creep rate is affected with respect to the grain microstructure. And the key question is, does grain microstructure affect fracture and creep behavior? So the materials used during this process was a gas atomized powder with the chemical makeup shown there. The powder that they used did meet ASTM standards. They tested all the powder before they completed the process, and they manufactured cylindrical rods with the EBM process with a diameter of 15 millimeters and a height of 85 millimeters. The process conditions examined were the microstructure of EBM rods straight out of the machine, and then they did an aging heat treatment on the same size rods, and they put they just did the creep behavior testing on the aged rods because they were interested in the microstructure after the aging process. The characterization tools were the RCAM A2 EBM system, which is shown on the right, and you can see that the bed raises and lowers, and it uses an electron beam to melt the powder, and the beam is controlled by magnets. And with the EBM process, you can have a higher power than laser-based processes, and you can obtain higher speeds because the melt rate is also faster. They also use electron backscatter diffraction to take measurements of their cross sections and to look at the grain microstructures, and they used transmission electron microscopy. So on this slide, I have some diagrams that they used the electron backscatter diffraction to measure different cross sections of the rods. The six graphs on the right are for the as EBM built rods, so those are straight out of the machine, whereas the graphs on the right were after an aging process, heat treated at 800 degrees Celsius for 24 hours. And what the different colors show are different phase lattice structures in the grain, in the rods. So the red is a gamma FCC or face-centered cubic microstructure, and the green shows an epsilon HCP or hexagonal close packed structure. The gamma structure, they said, was a metastable phase, so it's stable as long as it's not subjected to high loads or only minor disturbances. And the green is the epsilon phase, which is a more stable phase for this process. So their main takeaway from this was that aging the rods, you could get a change in the phase in the microstructure, but changing the microstructure actually decreases the grain size, and the grain size has a direct effect on the creep rate, which is on the next slide. So the grains are actually shown in the IPF map columns, and you can see that the grains are coarser where there is original epsilon and gamma phases mixed, but as they went through the heating or the aging process, the grain structure that changed from gamma phase straight to epsilon had a finer grain structure, and that affected the creep rate. So the second part of the study was to look at how the creep behavior was related to the microstructure. And they found that the finer grain structure had it had worse creep behavior because the fine grains had more grain boundaries per unit volume. So they determined that it was better to have a coarse grain structure, and the coarse grain structure was a direct result of having epsilon phase lattice structures original in the rods rather than going through the aging process and transforming it from gamma to epsilon. So the key conclusions in the paper were that through the aging process you can transform the phases, but it has a direct effect on grain microstructure, and the creep rupture life can be improved by increasing the grain size. So coarse grain is better than the fine grain. They said that the epsilon phase can increase more easily by growth of pre-existing epsilon grains rather than nucleation, which was shown on this slide at the top cross section, where it goes from gamma straight to epsilon rather than just growing the epsilon phase into a full epsilon phase. And they said that they were going to obtain coarse grains by a two-step aging heat treatment process, but they didn't really dive into how they were going to do that or what that two-step process was made up of. So my personal critique of the usefulness of this research is that the paper was well written and well organized, but there was a ton of information. It probably could have been 3 separate research papers. So it made it kind of difficult to decipher exactly what they were trying to accomplish and what was actually relevant information. The test conditions that they used during the creep testing were at 700 degrees Celsius and pressures greater than 240 megapascal, which I don't think would be applicable to knee or hip prosthesis, because I don't think your knee is going to see 700 degree temperatures, or you got worse problems than replacement failure. Yeah, in the introduction, they mentioned that EBM process and cobalt chromium was mostly used for hip and knee prosthesis. And they had one sentence that talked about the aluminum die casting, but they led you to believe it was mostly for prosthesis, for hip and knee replacement. But then they did their creep testing at 700 degrees and really high pressures. So I didn't really see the correlation there. But from what I took from it, it seemed like maybe this could be applied to tooling design for aluminum die casting.